Good afternoon, Physics 30. I hope you guys are having a good day so far. So, this video, we are going to be looking at electric fields. So, similar concept to kind of what we were doing last year with gravitational fields, except now we're going to be dealing with electric fields with a point charge. Okay? So, and the big difference as well is that with gravitational fields are attractive only. Whereas now with electric fields, they're repulsive or attractive. So therefore, we're going to have to keep some ideas in line with our field lines and that kind of thing. And because they can be either attractive or repulsive fields, it's going to change how you're going to be dealing with direction as well. And that's the tricky part. The equation isn't that hard. It's keeping together all of the bits with the vector fields and the directions. That's really the tricky part. So that's what I want you guys to be focusing on today while we're doing our video. Ready to rock? Oh yeah. Okay. So, ladies and gentlemen, the concept of fields, it was introduced to explain how two objects that aren't in contact with each other are still able to exert a force on each other. So why two similar charges repel, and why two similar or different charges are going to attract, and how gravity works, etc., even though they're not in contact with each other. So you could see fields as the definition are spheres of influence that are action at a distance or force applied at a distance. So a field that is going to have a specific direction involved is a vector field, and electric fields are vector fields. They do have a very specific direction involved. So like we did last year, when we looked at gravitational fields, they are vector fields as well. But because, remembering from last year, your gravitational fields are purely attractive. So the two masses are going to be pulling on each other. Okay? So remember with our field lines, for your gravitational fields, they are going to be pointing towards that object because your test body, or a mass that is put into this field, is going to be experiencing a force that is attracted towards it. Now, remember, all masses are going to be exerting a gravitational field. Why is my pen not so attracted to my face that it's just zooming across and sticking to the side of my face? It'd be kind of funny, actually. Why doesn't it do that? The masses are too small. Because when you remember our value of big G, that, the 6... It's on the back of your data sheet. I found my data sheet again. All right, so that one, 6.67. So remembering our big G is 6.67 times 10 to the power of negative 11. So that is your universal gravitational constant, or as I like to think of it, like one piece of gravity. It's not the best explanation for it, but that's kind of how I like to think of it, as one little piece of gravity, one unit of gravity. It's tiny. Like, it's absolutely tiny. So when you're weighing the mass and just plain old individual kilograms or grams, the gravitational fields are going to be so negligible that it's irrelevant. So that's why the pen is not going to be attracted to my face to the point it's sticking there. Okay. Although with all the titanium plates and screws in my jaw, at least I think I'd be able to stick magnets in my face, but I can't. I know. It's annoying. Well, magnetism is next chapter. Okay, so, ladies and gentlemen, the same way that a mass is going to have a gravitational field, every charge is going to create its electric field. Okay? Now, remember, ladies and gentlemen, these are vector fields, so that means directions are going to be very, very specific here. All right? And you're going to have to memorize this bit. All right? Electric fields, they're going to either radiate outward or away from positively charged objects. and radiate towards negatively charged objects. So what I need you guys to do is star that in your notes, put a sticky note in there with a note that says on test or memorize or something along those lines. Excuse me. So, ladies and gentlemen, that's the first thing to keep in mind. Note, these are positive charges here. Okay, so while we can think about it as if we draw our field lines, if our test body or object we're going to put into that field is going to be positive. So it would be a positively charged test body. Okay. So I've got a thing for circling my charges at a prof in university, an organic chem prof. If you didn't circle your charges, he would deduct points. So we had to circle our charges. So I'm like more than 10 years on. We're talking like 13, 14 years ago now. And I'm still obsessed with circling my charges. Frightened of points even now. So if we are going to place a positively charged object inside of an electric field that is created by a positively charged object, well, it's going to repel. All right? Okay, if we place a positively charged object inside a electric field created by a negatively charged object, it's going to attract. Sounds good? Okay, so another thing when drawing your field lines, the more dense the lines, the stronger the field. Okay, so these are really good. It's a very nice diagram that we've got here for you. So with this one, you can see the lines radiating outward of that positive charge. And this guy, whose positive charge is double this one, the lines are still radiating out, but notice how dense the lines are. And I'm going to switch colors here to blue, but notice here at that base, these lines are farther apart from each other than they are out here. So that is showing that closer you are to that object, the stronger that field is going to be. Just like with the gravitational field. And same over here, like the closer the lines are here, you're going to have the stronger field there closer to that object than you are out here. Sounds good? Okay, so with this diagram here, you've got that negatively charged object and you've got your field lines coming towards it. Any object you put in there with a positive charge is going to be attracted towards that. And once again, for line density, these lines here are farther apart than these lines. So this is a stronger field. Well, this has got double the negative charge of this first diagram. And then same farther away, the lines are farther apart, so therefore they're going to be less strong than that electric field. Cool beans? Okay, so less than subtle hint, you need to know those things. That will be on test. And the application of this piece here is going to come into your calculations. So this isn't just a theory question. When you are going to be getting your direction for your vector questions, because it's a vector field, I'm going to want direction. You're going to need to know that bit. Radio? Radio. Okay. So when we have field lines interacting, that's always cool. That is where you can really see how positive or like charges repel and how similar charges attract to each other. Okay. All right. So here you can see you have repelling going on here, and you have repelling going on here. I got an extra L. There we go. So with this, you can see how these field lines, it's two positive charges. Like, you can't have your field lines touching with a positive charge. They're going to go away. And here in the center, you are going to have no field. Okay, so in the center of those areas, there is no electric field there. All right? Okay, so when you have two different charges and your field lines, well, they're moving away from a positively charged object, well, those arrows are going to go right towards that negatively charged object. So if you place a positively charged object here, it's going to zip its way over that way towards that negatively charged object. Sounds good? Okay. All right, so let's look at our equation. Once again, all my vector arrows got turned wonky because the computer is a nutcase. All right. On your data sheet, but that's the periodic table. On your data sheet, you don't need the periodic table, it's the last unit. You're going to see the first equation that we're going to be looking at. Very, very similar to previous equations we've used both last year and this year. So the first equation is this guy here. I need to hold this better. There you go. Can I see? This guy. Okay. And that's the one we were using in the previous videos when I couldn't find my data sheet because it was under the writing tablet. I thought I'd left it at school, but it's under the fancy writing tablet I'm using on my right here. So our equation is E with the arrow over top is our electric field strength, and its units are newtons per coulomb. And it's K Q over R squared. All right. Okay. And K, Coulomb's constant, right on the back of that data sheet, so you don't need to memorize that number. Okay. K is right there. Okay. And Q in this equation is the object producing the electric field. I want you guys to highlight this here because we're going to be dealing with all sorts of different Qs. All right. Okay. So this is the Q, the charge of that object producing the field. Okay. Okay. Units, coulombs. R is the distance from the charge producing the electric field. So it doesn't have to be an object. It could be like a point. So if you have, here's your positively charged object, and we could say at point P, that's often what is used as point P, just random point. That is the distance there from the source to whatever point you happen to be in the field. So similar to last year where it'd be just a certain distance from that planet or what have you. Okay. So ladies and gentlemen, from that equation, you are going to see, like we've already done before, you can see a really nice inverse squared relationship. Okay. Between the strength of that electric field and the radius. All right. So your electric field, inverse squared relationship. All right. So how do I graph this? Like that. How would I make this a straight line? How would I straighten this graph? Have to make it match the equation. That would be a straight line. Then I could calculate the slope of that line and I can do all sorts of cool stuff. Sounds good? Okay. So, ladies and gentlemen, remembering back to last year, we've got your gravitational field. So, very similar equation. You've seen that equation before, and once again, if you weren't able to quite get all of this super well because of the shutdown last year at the time of filming, I have no idea how far in the future you guys are actually going to be using these videos. But you can go back onto my YouTube channel and rewatch that video lesson, or come see me in Focus or what have you, and we can get you caught up with there if any of this is causing you grief. All right. Okay. So same idea, how your gravitational field strength is going to be an inverse squared relationship. Okay. So, whoops, that's not FG. That's going to be little g. There we go. Okay. Alrighty, now. So, ladies and gentlemen, we do have another equation that we're going to look at here. Now, this one is a nice, handy, quick little equation that is nice and easy to use and can be used in all sorts of different scenarios. So, electric field strength can be calculated on the force of another charged object will experience if you're going to stick it inside of that field. Okay, so if you are going to have your field that is going to be producing a charge, and then you can stick another charged object in there, well, you can calculate the strength of the electric field using that force. Okay, so your equation is on your data sheet, which is right here. Okay, so your force electric over your Q is going to equal your electric field strength. Okay? All right. So E, newtons per coulomb, is the electric field strength. Fe, electrical force. And Q, this is the tricky part, is the charge of the object in the electric field. Okay? Okay. I want to show you guys something really cool with this equation. I just love it. All right. So, ladies and gentlemen, remember, I'm going to rearrange this equation so that way EQ is going to equal FE. Okay? Okay. And then what is our other equation for FE? Well, K Q1 Q2 over R squared. Well, what is the equation that we just looked at above? Well, it was KQ over R squared. Well, here we've got that other Q. Well, I can just label that one and that two. What do you guys notice? They're the same. So, once I finish writing this out, Q1, Q2 over R squared is equal to K Q1, Q2 over R squared. So this equation here is just a nice, simplified, handy-dandy, easy-use version of this. Isn't that awesome? I love it! I absolutely love stuff like that. It's just so much fun. It's awesome. And it shows why it works, too. Like, I really like it when you can link the two equations. Can you tell I enjoy this? A little bit. Okay. All right. Ladies and gentlemen, let us put these equations into action. So the first thing we're going to do... Oh, one thing I also forgot to notice, guys. Forgot to write this down because it's what I do. The same thing that we do with with all of our other equations, with electric fields and forces and all that jazz, absolute values. Okay, so the exact same way we use absolute values in our electric forces, we're going to use absolute values in our electric fields, and we are going to use our vector field lines to give us our directions. Okay, so same as up here, we're going to add our absolute values. Drop my S. Aren't you glad I don't teach English? Considering how messy my writing is. I'm glad I don't teach art either. I've never taught English, but I have taught art once. So bad. Felt so bad for those kids. And stuck with me for art. Okay. That was almost as bad as me teaching phys ed. Yeah, I'm not a phys ed teacher. I was that kid in gym class who ran back and forth, yelling, "The ball, I'm open," while everybody ignored me because I sucked so bad because I couldn't catch that arm ball. Yeah, I was that kid. All right. So, ladies and gentlemen, if the distance from a point charge is tripled, ratios. And the charge on the point charge is also triple. By what factor does the electric field strength change? Oh, here we go. Factors, ratios. Awesome. Now, in this case, we don't have an original value to start with, but we've been only asked for the factor. Okay? So, what we're going to do is we are going to start it out as our original and modified again. Okay, so we know we have an electric field. Okay, we know that the distance, okay, we have a distance, and we know that we have a charge. We don't have any actual values for them, but we also know that E is equal to KQ over R squared. That's all we got. Okay, but that's all we need. So therefore, we're going to go to our modified. And then we are going to have E K Q over R squared is our equation we're going to be looking with. But ladies and gentlemen, we need to find, like, we don't have E prime, okay? That's what we're trying to find. What's it going to change by? What is the factor E prime is going to change by? We know the Q prime is what? Tripled. But it's 3 times of what it was. So we can't just put 3. It's got to be 3Q. And then what next? Radius is also tripled. So our radius prime is going to be 3R. So let's take these values and plunk them into our equation. Okay, watch that denominator there. That 3R has to go inside the brackets, okay? All right, so what we're now going to do is we can solve for that. So we'd have K 3Q over 9R squared, because this square has to count for both of those. And then, well, I can now factor out the 3 over 9. There we go. So, ladies and gentlemen, how can I simplify 3 over 9? It's a third. Okay, so therefore, E, okay, is going to change to a third of what it was. Cool beans? There we go. 3 dots in a triangle like that means therefore. Very rarely do chemists and physicists and mathematicians like actually writing in full sentences. We like the abbreviations. And we tend to write very bluntly. Like any of my writing is like a lab report. Like it is blunt as a sack of hammers. So it's not pretty, but kabam! Information! Like a lab report. Okay. So that is our factoring question. So now we're going to get into a couple trickier questions here. Now remember what I said earlier, the equations aren't the hard part here. It's getting the direction and figuring out what is happening with our vector fields here. That's the tough part. Okay? Okay. So pay particularly close attention to when I'm talking about directions, because that's the tough part. All right, determine the electric field strength 7 meters south of a negative 8.50 microcoulomb charged object. Okay, so ladies and gentlemen, this sounds kind of weird. It sounds awkward. We're south of a negative 8.5 microcoulomb object. Draw it. Trust me. Draw this. So here is your object. It has a negative charge. Okay, now let's draw the field lines for this. Okay, where are the field lines going to go? Towards this or away from this? Where are they going to go? towards. They're going to go towards this object because why? Where it's as if we have a positive point charge, a positive object placed into that field, a positive test body. So your field lines have to go towards this guy. And now we are going to be 0.7 meters south of that. So point P is going to be south of this charge. Well, look where the field lines are going. The field lines are going north of point P. So that means our direction for this, we just happen to figure out our direction first, is going to be north. Okay? Okay, because it's a vector field. When we say field strength, as the field strength is a vector, I need to have a direction. All right? Okay. So our next piece here is, well, determine the electric field strength. Well, we have this, which we're going to convert into our appropriate units. Okay, this is already in good units. We've got this. We've got a charge. Okay, so E is equal to KQ over R squared. And our K is 8.99 times 10 to the power of negative 6. And Q is our charge of, once again, absolute values, 8.5 times 10 to the power of negative 6 coulombs. Divide by that, this is already in meters, of 0.7 squared. And you're going to get your field strength. I dropped a 4. No, I didn't. We're good. I did not drop a 4. Okay. So we have this value. How many sig digs do I want? 3. Okay, we want 3 sig digs. So I'm going to need to put this into scientific notation. 1, 2, 3, 4, 5. So I'm going to look at my rounding here. So I want 3 sig digs. So I'm going to come back and look at these guys. This 9 will round that 6 up. So I'm going to have 1.56 times 10 to the power of 5 newtons per coulomb. All right. And my direction, north. We figured that out first. It doesn't really matter what order you solve for your direction and your, and your magnitude in this particular question. All right. Good to go? All right. So let's do another one. So a positive 5 microcoulombs, so that's 5 times 10 to the power of negative 6 coulombs. Charged object is placed in an electric field of 2.20 times 10 to the 4 newtons per coulomb to the east. Determine the electric force acting on the charge. Now notice I didn't say magnitude. Force is a vector, so therefore I'm going to want direction. All right. So ladies and gentlemen, the hardest part about this question is going to be the direction. So once again, I could either find direction first or magnitude first. It doesn't matter. I'll shake it up a bit. I'll do magnitude first. So I've got Q of 5 times 10 to the power of negative 6. Whoops, I nearly wrote my wrong units. I would have cost myself half a point if that was the final answer. And then we've got our K as always, and we have our force of 2.2 times 10 to the power of 4 newtons per coulomb. And then, oh goodness, that's the field strength. That was silly. There we go. That's better. Okay, and we're trying to find the electric force. You would think it's Monday, but it's not. It's Sunday today, so you can't even blame Monday. No, Sunday when I'm filming. You guys could be watching it any day of the week. So you could be watching this on a Monday. Therefore, it's Monday. Okay, so looking at our values, well, guess what equation we can use? E is equal to Fe over Q. Now remember that this Q here is the charged object in the electric field. We can use this equation because Q here is in the field, and it says that specifically in the question. All right? Okay. So we are going to rearrange our equation. Fe is equal to EQ. I'm going to plunk in my numbers of 2.2 times 10 to the power of 4 newtons per coulomb. And I'm going to multiply that by 5 times 10 to the power of negative 6 coulombs. Coulombs cancel in your units. And we're going to wind up with the lovely answer of 0.11 newtons. I get my units wrong. I nearly cost myself half a point again. Goodness. All right. So, ladies and gentlemen, let us now talk about direction. This is the hard part. Okay. So, a positively 5 charged object is placed in an electric field with a direction to the east. Okay. So, ladies and gentlemen, my field lines are going to the east. Those red lines are my field lines. What are the 2 possible cases in which I can get my electric field lines going that way? How would I arrange some point charges? I'm going to switch to blue here. Well, I could place a sphere, or it doesn't have to be a sphere, any charged object here. What would this charge have to be if its field lines are going this way? They're going away from it. Positive. Remember that the field lines are going to go away from a positively charged object. Okay? All right. Well, what if I put an object here? Because this is the second scenario. What charge would this object be if over here if I want to get field lines going to the east? Negative. This could be a negatively charged object and still have field lines going towards the east. Well, I am placing a positively charged object inside this field. We'll change colors. Let's go pink because pink is cool. I'm going to put a positively charged object inside this field. Now, what's going to happen? It's going to go to the right. It doesn't matter, or in this case, east. It's going to go to the east. It doesn't matter if this is a positively charged object that's creating the field, because the 2 positive charges are going to repel each other, and that pink object is still going to go to the east. Whereas if that we get rid of, I nearly covered up that positive thing. You can't see that I'm covering the positive thing on the screen. So cover up the positive charge on the screen, and then you can see the field lines going towards that negatively charged object. And with that, you are still going to get that positive charge moving towards the east, because that positive charge is attracted to that negative charge. Sounds good? Okay. So that means our direction is going to be east. Sounds good? Okay, so you guys can see that the toughest part here is not the equation. The equation is the easy part of this question. The tricky part is getting that theory to dance with your equation. Okay? All right. Alrighty-o. So, ladies and gentlemen, one more question, and then the video will be done. It's freezing in here. It's really cold today. I have to walk the dog after this. Because Freya is going to be restless. Okay. So what is the electric field strength? Okay. Midway between charged objects of negative 3.5 microcoulombs and 3 microcoulombs placed 0.440 meters apart. Okay. We're going to have interacting fields here. Okay. So, ladies and gentlemen, let us get our setup and draw it. Drawing it's going to make your life so much easier. I'm going to start with this guy here. I'm going to make this guy my negative charge. Okay. So, here is this guy. He's negative. He's got a Q of negative 3.5 times 10 to the power of negative 6 coulombs. And I am looking at a point midway here. Okay, so that's point P and placed 0.440 meters apart. Okay, and this guy is Q. It's going to be 3 times 10 to the power of negative 6 coulombs. Okay? Okay. So, let us think. What is the radius that we need to use? 0.22. Because we're dealing with two separate distances here. We're focusing on point P. And it says midway. It's halfway in between these two. Okay. So that's one of the little picky details that you guys really, really got to watch for in these questions are things like midway. Okay. So that's going to change how you're going to approach this. So your logic is going to be a huge part of what we do here. All right. Okay. So, ladies and gentlemen, I'm going to call this one, call that 2, because I can. And I'm going to find my electric field strength, okay, at 1. That 1 is causing at point P, the effect of that there. And I'm going to start with just magnitude, okay? We'll worry about direction after. So K, Q1 over R squared. K from your data booklet is 8.99 times 10 to the power of 9. And Q as once again, absolute values. Okay. 3.5 times 10 to the power of negative 6. Divide that by our 0.22, square it. And we're going to get the magnitude of 6.5013 times 10 to the power of 5 newtons a coulomb. Okay. So I will come back and do direction afterwards. Okay. So that way we can really, really think about direction all at once. In the scenario of a test or a quiz or an assignment or whatever, you guys can do it in any order you want. You can do direction now if you want, but I'm just going to do it after, so we just for the sake of the lesson, so we can really, really hone in on that direction stuff, because that's the tricky part. I was like, this equation itself isn't too hard, so it's not the hardest part of the question. So then we have our K Q2 over R squared. Plonk your numbers in. K's off your data sheet. Okay. This one is going to be 3 times 10 to the power of negative 6. Divide that by your 0.22 squared. Plonk that into your calculator. My answer's on the computer here to my right. Because I already did this stuff before I started filming. It's on the computer. Okay, and there we go. Okay, we have our magnitudes. Now remember the same way that we were finding net gravitational fields last year and how we were finding net electric forces last video or last lesson, we're going to need to be adding these guys together. So direction is going to matter here. So let's think about our field lines. I'm going to go green because I can. So let's start with this guy here. Now I've got a negative field or negative charge here. What direction do my field lines go on a negative charge? Towards it. So that means my field line is going to be going this way from the perspective of point P. Now, once again, like we still have the rest of these field lines here, but the rest of these guys are not relevant to our question. So we are only going to be focusing on point P alone. Now, let us look at this guy here. Well, here we've got a positive charge. And what direction do field lines go for positive charges? Sorry, my computer's reminding me that I don't know, some type of storage is used up. It was like the cloud or something. I don't know. Anyway, so it's flinging things on the screen, covering my physics. So what direction do these field lines go? Positive charge. Away. So that means your arrow is going to go there. Well, will you look at this, ladies and gentlemen? What direction are these guys going in? Left. So once again, it doesn't matter whether you choose to make left positive or negative. I mean, for the sake of ease, because they're both going left, I'm just going to make left positive because I don't feel like dealing with negatives because why? I don't have to deal with negatives here, so I'm not going to. Make your negatives work for you. Okay. So, well, now I am going to find my E net at point P, and which is going to be E1 plus E2. Add them together. So I've chosen to make left positive, so therefore they're positive. If you choose to make left negative, rock on, make left negative. I'm just choosing to make them positive. So 6.5013 times 10 to the power of 5 plus 5.572 times 10 to the power of 5 newtons a coulomb. Add them together, and you get 1.20733 and times 10 to the power of 6 newtons a coulomb. Well, as always, sig digs and units and direction. So what we got here is you look back at the original question, how many sig digs do I want? Three sig digs. So I am going to look at my values here. This is a 7. So I'm going to come over and look 1, 2, 3 sig digs. I look at my next ones. That 7 rounds that guy up. So I have 1.21 times 10 to the power of 6 newtons a coulomb. And what direction did we determine this to be? Because this is now positive and we decided left is positive. Our direction is left. Okay. So, ladies and gentlemen, There we go. That is today's lesson. Now I know that there are definitely some tricky bits in this one, especially when you are looking at those directions. So really, really pay attention with these questions. And in order for you to master your skills with this, there are your practice problems at the bottom. Give those a try. See how you do. Check your answers. If you have questions, come see me in Focus, room 236. And we will see you all later. No fires, injuries, or explosions. Stay away from rampaging viruses, please. Talk to you guys later. Bye.